If you will recall, when we originally defined current, we said that current was the result of a bunch of charged particles having net motion. The formula we used was current is equal to number density of electrons times the charge of an electron times the average drift velocity times the cross-sectional area of a wire. If a bunch of charged particles have a net motion inside of a magnetic field, then this collection of particles will experience a net force that is the sum of the individual forces. To find what this is, first, let's multiply current by the length of a segment of wire. And so we get this quantity is equal to NEAL times V. Now since N is the number density of electrons, and E is the charge of an electron, and cross-sectional area times length is equal to volume, volume times number density is equal to number of electrons times the charge of a single electron gives you the total charge in that segment. So I times L is equal to Q times V. Since the magnetic force is F is equal to QVB, we can similarly say, since QV is equal to IL, the force on a wire is equal to ILB, where I is the current in the wire, L is the length of that wire, and B is the magnetic field. Now, if we were going to do this all properly with vectors, we would say the force vector is equal to the current times the length vector of the wire crossed into the magnetic field vector. The rules of the cross product are the same as they were for F is equal to QVB. Because a wire is an extended object, this equation only holds true if the magnetic field is constant. If the magnetic field changes with position, then we are going to have to do a bit of calculus. First, let's break up everything into little pieces. And that gives us dF, a small piece of force, is equal to I times dL, a small piece of the wire, times B, cross B. Now we add those pieces together, and we get that the total amount of force, all these little dFs added together, is equal to the integral of I dL cross B. Now I know you are used to seeing the d term at the end of an integral. I assure you we are allowed to do this, and because the cross product does not commute, meaning the order of the cross terms matter, we have to do this. But the b is a part of the integral. Now Kirchhoff's current law says that the total current going into a node, if you add up all of those currents, that should be 0. When we apply Kirchhoff's current law to a single wire, that means that current is constant through all points of the wire. Since current is constant, we can pull it out of the integral, and we get that the total force is equal to the current times the integral of dl cross b. In general, this can describe a wire doing anything it wants through any magnetic field it wants. However, for the purpose of this class, I am going to assume that the wires are generally easy to integrate. This usually means that they don't curve, and that they have a fixed direction relative to the magnetic field. In which case, we can simplify this formula into F is equal to I sine theta times integral of B dl. Now because we are using the scalar form, scalar multiplication is commutative, that's why I am able to move the dl here to the end. And once again, theta is the angle between the wire and the magnetic field. Again, it is a scalar, but force is ultimately a vector, so you may need to find the force, And again, you will use the right-hand rule. This time, since L is the first term, you use your thumb in the direction of the length vector, and your fingers are still in the direction of the magnetic field vector. Now, one thing I could do, and that's not too terribly difficult, is to give you a wire that is composed of a number of different straight sections, with sharp corners in between them. In that case, what you want to do is you want to find the force acting on each individual chunk of wire, and then add all those pieces together. Again, remembering force is a vector, you need to add them as vectors.